Hello, everyone. Thank you very much for joining us. We are excited to be with you today. My name is Matthew. I'm one of the course staff, and Victoria is behind the scenes today managing our Twitch stream. And I will let Professor Impey say good morning or good evening, depending on where you are in the world, and then we'll get started with questions.
Yes, welcome everyone to another live session with online astronomy classes, and let's get straight to it. Floor is open for your questions.
Excellent, thank you very much. Vicky, I just want to let you know that we can hear clicking, so I'm not sure if you're muted, but it's okay, I'm just letting you know. So the very first question today is from one of our emails. Peter Bayfus says, there was much talk in the 1970s about developing an alternative, safer energy source than nuclear fission, which is nuclear fusion. What's the latest thinking on the feasibility of building one of these reactors that works like a star?
It's kind of discouragingly slow progress. So fusion research has been ongoing around the world for, almost half a century. And the goal of sustainable energy production for a reasonable amount of time has just not been achieved. The problem is easy to state in principle. To make fusion occur, you need temperature that is so high that no container exists, no material exists to contain the fusion. And so people are essentially using magnetic bottles. And it is very hard to use a magnetized plasma to create a containment device. The tokamak design, which is a sort of toroidal magnetic containment design, has been dominant for a few decades. But even with that, and with many countries working on this, the U.S. investment is a few $100 million a year. All that's been achieved is, fractions of a second of sustainable energy production. In principle, it's a great energy source because it's clean. It takes hydrogen and turns it into deuterium or helium, just as the sun does. So there's no radioactive byproducts and no radioactive materials involved at all. So that's the upside. The downside is the physical conditions required to create a viable reactor are extreme. They're extraordinary. They happen effortlessly in every main sequence star, but it's not easy to do on the Earth. So basically, because the cost of renewable energy sources has come down so much, wind and solar in particular, to now rival that of fossil fuels, fusion power has sort of receded as a likely use, as a likely source of alternative energy in the future, because the investment costs are still too large. So that research continues because it has other spin-offs in physics, but I don't think we're looking at any viable fusion reactors in the next few decades.
Excellent, thank you very much. The next question is from one of our online participants, one of our live viewers. And just so that everybody knows, you just have to ask the questions one time. We can see them. And if we start getting spam in the channel, we're gonna we have to delete questions so that we can see everything. But the first question is from Student McLeod, who says, should living cells be detected on Mars, what assurance will we have that they are not terrestrial cells transferred to Mars by Earth origin meteors?
Right. That's an interesting question, or indeed by the spacecraft that goes to Mars. So they're in looking for life in the solar system, particularly the two issues are forward and back contamination. The forward contamination is we bring microbes to Mars, say, and inadvertently contaminate it, and then look at life that's basically things we carried there. Back contamination is a concern. If we find microbes on Mars, bring them back to the Earth, how will we keep ourselves safe from these microbes, which may be pathogens? The question, and these are significant issues, and NASA takes them very seriously. So basically, there are sterilization procedures, which happens quite naturally in Mars, because even though the atmosphere is thin, spacecraft entering the Martian atmosphere at very high speed are sterilized. So the exterior of a spacecraft is sterilized, and the interior and payload can be sterilized before it leaves the Earth. So this kind of contamination is pretty much being addressed. The contamination that you're asking about, where possibly a microbe-bearing rock could leave the Earth and go to Mars, is a significant possibility. It's very hard to attach a probability to it. We know that Mars rocks come to the Earth. We have close to 100 Martian meteorites identified, and obviously there are many more than that that we don't know of yet. It turns out that the reverse process is less likely and happens far less often. Martian meteorites get to the Earth because Mars has low-ish gravity, a thin atmosphere, and of course the sun is in the direction of the travel from Mars to the Earth, so it's gravitationally a favorable situation. The reverse process is unfavorable in three different ways. The Earth's gravity is higher, its atmosphere is thicker, and you're going against the sun's gravity to get to Mars. So for all of these reasons, terrestrial microbe-bearing rocks getting to Mars is a very unlikely process. That's not to say it couldn't have happened, but it's unlikely enough that in most calculations it's not something realistically worth worrying about.
Excellent. Thank you very much. The next question is from an email. Wendy Traver asks, if according to the Big Bang Theory, everything came into existence at that time, wouldn't that make inflation and dark energy different aspects of the same phenomenon? That is, inflation was a manifestation of what we call dark energy today, since both of them forced the universe apart.
It's an interesting question. So we don't really know. We don't know enough about dark energy really to speculate. And equally for inflation, we're a little uncertain too. The main issue in inflation, if inflation actually did happen, and there's some evidence that it did, that the universe went through an early state, a tiny fraction of a second after the Big Bang, of exponential expansion, which essentially flattened and smoothed out the universe to be the way we see it now. The agent for the inflation, the field, if you like, or the force for the inflation, presumably from the vacuum of space, a precursor condition, has not been identified in physics. And the same is true of dark energy. So these are things we're almost equally ignorant of. It's a little tempting to compare them because the dark energy in the universe now is causing accelerated expansion, and inflation, whatever it was caused by, was an early state of accelerated expansion. And yes, some people have tried to do that physically. But the truth is there's no underlying physical mechanism that we can verify for either inflation or dark energy. So comparing them and imagining they might be the same cause is interesting, but until there's a viable physical theory, it's just more speculation.
Excellent. Thank you very much. The next question is from Dumbledore 1995. How do we determine where is up and down in space?
Good question. And basically, you don't. There's no up or down in space. We have up and down on the Earth, and even up and down on the Earth is a relative thing because wherever you happen to be on the Earth's surface, there are obviously people diametrically opposed on the planet for whom up is the opposite to what it is for you. So on the Earth, up is just defined by local gravity. And in the rest of the universe, the solar system or the galaxy or the larger universe, equally, there's no preferred orientation or sense of direction. And in a sense, this is a statement on large scales of the isotropy of the universe, that the universe is more or less the same looking out from the Earth to large distances and large look-back times. It's the same in every direction. So based on our view of the universe, there is no preferred direction, and therefore the corollary of that is there's no sense of up or down for the universe as a whole.
The next question is from Ayan Gowan Senpai 987. Adaptive optics changes the surface of the secondary mirror on the fly to adjust for distorted wavefronts. How and what do they detect to use as input to control that so rapidly?
Yeah, it's a good question. So adaptive optics does indeed tend to work typically on a secondary mirror because the secondary mirrors are much smaller than the primary mirrors. But for today's largest telescopes, a secondary mirror is a meter or more in size. So adjusting the surface of a very thin shelled meter secondary mirror dozens, maybe 50 or 100 times a second at 100 hertz, that's a challenging job done with piezoelectric actuators. At the University of Arizona, where we make adaptive secondaries, there's typically 140 or 150 rapid response piezoelectric actuators, and those are the devices that control the surface of the mirror. So the reference for this, and therefore the reference for taking out the turbulent effects of the atmosphere, has to be by showing what the atmosphere is doing. And that's typically done with a laser. So we use sodium lasers, and other observatories use similar lasers. They're quite powerful. They're 100 watt. These are quite dangerous devices if you had them in the lab. They're pointing up in the sky, and they're not in a very focused beam, so there's no danger involved. These lasers are designed to reflect off the upper atmospheric layer where most of the turbulent motions occur. It's in the mesosphere, so it's above the layer, the immediate weather layer, in a slightly larger range of distances upwards. And then the backscattered laser light is collected by a telescope, and since the laser light is coherent and travels out in one wavefront, the variations in the wavefront of the backscattered light will reflect the variations in the wavefront caused by turbulent motions in the atmosphere. And so it's that reflected laser light that forms the reference with which the secondary mirror is adjusted. And obviously it has to be done frequently because these atmospheric motions are fairly rapid. Most of the motion happens on a time scale of maybe 1/10 of a second, so 10 hertz is good for getting most of the motion, but to get the high frequency components, the speckle and the jitter, you actually have to go up to 30 or 50 hertz. So it's by referencing a laser off the same atmospheric layer that's causing the jumbling of the star's light.
Someone in the chat just mentioned that I got the time wrong for Eastern Standard Time, and I apologize, everybody. I'll make sure that I have my my daylight savings time fixed for next time. Parzival Fusto asks, Apophis is going to crash on Earth by 2068. What is your opinion for mankind?
Yeah, that's not a certain statement, actually. Apophis has a significant probability of going through a keyhole gravitational window and therefore being in a very likely Earth-crossing trajectory. But that very likely or quite likely is a probabilistic statement, and we simply don't, until the time gets closer and the orbit is measured well. We can say what the orbit or the trajectory of this object is now, but over a period of time, especially decades into the future, these projections are not completely reliable because the orbit can be perturbed by gravitational interactions or encounters with other objects. So essentially, there'll be no better sense of a probability of impact until much closer to the time. So let's just leave it at the level where there's a significant, maybe even substantial probability of impact, certainly not a certainty. But we will keep our eye on it, and it is a large enough object to cause regional devastation, I think. It's a fair statement, traveling at tens of thousands of miles per hour. We do have recourses. I mean, we have technologies with which to either deflect or destroy an inbound object if we have enough warning. And for an object like this, where it's already being monitored, I think we'll have plenty of warning.
Thank you very much. The next question is from Alexandria 597. What is the perspective of space tourism development in the near future? And would you go into space as a tourist if it was possible?
Yeah, to answer the last question first, sure, I would. I mean, it depends on the cost. And as for the holiday of a lifetime, I'd be willing to pay some significant amount. I wouldn't bankrupt myself or spend all my retirement on it for sure. But if it comes down into the range, you know, I don't know, $30,000, $50,000, which is a very expensive cruise or holiday that people already take now at the high end, yeah, for going into space, I would definitely consider it. The prospects for space tourism have ebbed and flowed over the last decade, but currently they're on a forward momentum track, and that's because Virgin Galactic has had the worst issues because they had a fatal crash of their test plane a couple of years ago, and they were grounded essentially by the FAA and forced to fix some procedural and some technical problems. They haven't had another flight for a few years, and I think their next test flight is pushed off into next year, 2021 at the earliest. So Virgin Galactic's path to what are essentially, you know, 10-minute zero gravity joyrides into the formal definition of space are going to come, and they've taken millions, tens of millions of dollars actually of deposits. So I think those will happen in 2022, 23 for the most part. The other big players, of course, are Elon Musk with SpaceX and Jeff Bezos with Blue Origins. They're busy right now making their companies economically viable by taking multi-billion-dollar contracts from NASA to resupply the space station and to get American astronauts into orbit, which the US government doesn't have the capability to do. So at the moment, they're busy paying the bills, paying their investors, and establishing viable companies based on that kind of work. But they both, of course, have plans for orbital flight. Once they can get astronauts safely into orbit, and they've done that multiple times, they will be easily able to take tourists into orbit. The prices for this are not quite clear yet. They're likely to be in the 100 to 200,000, maybe more, dollar range. But this is going to happen. So I would say within 5 to 7 years, we will start to see the beginnings of a completely economically viable space tourism industry.
The next question is from QZ0IM Qzom. Can we build nuclear power plants on the moon, and how beneficial would it be?
Power plants on the moon is certainly something that's been proposed and talked about, and it's based, of course, on colonization of the moon. So if we want either to have a viable long-term colony, or maybe more likely just to have a viable industrial presence and establish a base for doing mostly robotic operations, then we'd need local power sources. Solar power, of course, is always available on the moon as it is on the Earth, but perhaps in some cases more power would be needed. There's interesting work been done just in the last 5 or 6 years on miniaturized power plants, and by this I mean fission reactors. Fission reactors, which traditionally are large, expensive, and somewhat dangerous. There's been real good work in miniaturizing these technologies to the size of a large car, for example. And I think these small-scale nuclear plants would be very appropriate for use on a place like the moon, because you'd essentially just put them there and switch them on, and they would work. So that's definitely a mode of power that you would use to establish a moon colony or a lunar industrial activity. And the same might be true on Mars, although it's a lot more expensive to get the makings of a fission reactor to Mars.
The next question is from Rasha. The Voyager spacecraft detected an increase in the density of space beyond the solar system. What could be the possible reasons for something like that?
Yeah, the Voyager spacecraft is one of 4 man-made objects that have left the formal solar system. Both the Voyagers 1 and 2 and the Pioneers 10 and 11 spacecraft launched in the 1970s have now exited the solar system. The Voyager spacecraft has actually traveled into what's called the heliopause, and that's the region where the sun, the solar radiation, solar energy from the sun hits a much lower density medium, or moves into a lower density medium and hits the ambient interstellar medium. And it creates essentially a sort of mild shock wave. And that increase in density caused by that interaction, that boundary layer between the solar wind and the interstellar medium, is what the increase in density that Voyager measured was. It was a very exciting discovery, because until then, measured directly with a spacecraft, it was just pure speculation as to what we would see when you hit the formal edge of the solar system. And maybe if the power continues for these spacecraft, of course it's dwindling rapidly over time, they may give us further discoveries of the nature of the interstellar medium.
Excellent. The next question is from Arcana, or Archana S, who sent an email. I have heard that the presence of astronauts on the moon could cause the moon's temperature to rise by 3.5 degrees Celsius. Is that true? And if so, how and what are the effects that it would cause if humans ever colonize the moon?
So I'm not sure it's an issue or a problem. So the issue of what would be the impact of human habitation or activity on the moon to the moon's temperature. For the most part, there would be very little impact, because remember, the moon doesn't have an atmosphere. So any human activity generating heat, humans of course generate heat, and the industrial activity they might be doing there, building things and powering places to live, will certainly generate heat. But this heat is essentially radiated into space. So the infrared radiation from human activity on the moon essentially radiates almost perfectly out into the vacuum of space. It doesn't not, in other words, is not retained by the planet. So the planet's surface itself is not noticeably being heated by human presence. Now that's only, the only violation of that would be if humans live, say, underground, or if they establish mines or other activities that actually do put heat into the surface of the planet, of the moon. But the moon is a large object, and so the odds of human activity in any foreseeable future changing the global temperature of the moon are very low.
The next question is from Nasty T19. How do all the spacecraft stay in orbit without crashing? The space industry is increasing and more spacecrafts like satellites will be launched into space. And so how do they, I guess, how do they stay in orbit without crashing into each other and then also without falling out of the sky?
Well, the basics of orbital flight are simply defined by gravity. The escape velocity, the circular velocity of the Earth is well defined, as is the escape velocity. So it's 11 kilometers per second for something to leave the Earth's gravity entirely, and 8 kilometers per second for something to go into Earth orbit. So if you give enough energy to anything and give it that velocity, then it'll go into a circular orbit. So the two issues of what happens to something put in Earth orbit, first of all, it depends on where in the orbit, where in the distance from the Earth it is. The problem comes in a low Earth orbit. So low Earth orbits are around the range of a few hundred kilometers up from the Earth's surface. And in low Earth orbit, there are two problems. One is there's an increasing amount of stuff there. There are dozens, literally hundreds of satellites, and the number will become thousands soon. And so the odds of collisions leading to shrapnel, and the shrapnel can destroy and spread over a larger region and therefore destroy other objects, that is steadily increasing over time with no real remedy, actually. So that is one way, not the nice way, that a satellite might come down. It may literally be destroyed in orbit by an impact. The other way is that when you're in a very low Earth orbit like that, while it is a exceptionally good vacuum, it's not a perfect vacuum. So the very small amount of air molecules that exist at those altitudes creates a small amount of drag on any satellite. And that drag gradually will degrade the orbit and eventually makes it fall to Earth and burn up in the atmosphere and fall into the ocean or on the land. This is particularly true of these constellations of microsatellites that are being launched by SpaceX and other companies for telecommunication purposes, for wireless internet, for example. These are delivered into very low Earth orbit, and they were almost by design are transient objects. They only exist in their orbit for 5 to 10 years before decaying and falling to Earth, and they have to be continuously replenished.
Thank you very much. The next question is from, Parsival Fusto says that 2 hours ago, Hubble saw an event called a kilonova. Can you explain what a kilonova is and why we're looking for them?
Kilonova is a mild form, as the word would imply, a mild form of supernova. Supernovas come in two types: the detonation of an extremely massive single star at the end of its life, or the detonation of a companion to a star as it's pushed over the Chandrasekhar limit and so collapses and detonates as a supernova. Now, kilonovas are intermediate. A nova is a variable star which has instabilities and flares. Its fusion reaction rate can change dramatically over time, and episodically it can flare up and create a large amount of energy. So a kilonova is sort of an extreme form of nova, but it's not as luminous or as dramatic as a supernova, and it's not the end state or death state of a star. A nova is a recurring object, very occasionally regularly, usually irregularly recurring in this flare, and a kilonova is that kind of object.
All right, the next question is from one of our live viewers, Mover and Shakers 707. If the universe is flat, as cosmologists say, then what is its thickness? I think this is a great opportunity to talk about the difference between flatness in that sense and the flatness in sort of a three-dimensional sense.
Right. So flatness, astronomers and cosmologists use flatness in a very particular sense, and they're essentially talking about the geometry of space-time, three-dimensional space-time. So we shouldn't think of flatness as in a piece of paper or a tabletop. This is the flatness of three-dimensional space. Now what that means and so it has no real relation to thickness, which is another sort of attribute of a two-dimensional object. It has thickness in three-dimensional space. So what does flatness mean in cosmology? Flatness means, do a little thought experiment. Imagine you send parallel beams of light through space, through the universe. If the universe is flat, spatially flat in 3 dimensions, those parallel beams of light stay parallel, no matter how far they travel. Billions of years later, they'll still be traveling parallel. And that's essentially like drawing parallel lines on a sheet of paper in 2 dimensions. The parallel lines stay parallel, never converge, always stay the same distance apart. If space is not flat, however, only one of 2 things can happen. The light beams that were sent out parallel can either gradually converge, move towards each other, or gradually diverge and move away from each other. The former is positively curved space, and the latter is negatively curved space. So there are 3 possibilities for what light can do traveling through the universe. And what the evidence is, so this is not a speculation or a theory, this is based on observation in the microwave background, the universe is indeed spatially flat. That is, those parallel beams of light traveling large distances through the universe stay parallel, and there's no curvature seen.
The next question is from Mohan46. Is there a center of the universe, and how fast is the universe expanding?
There's no center of the universe. Although galaxies are all receding from us, the redshift, which is recession velocity of galaxies, almost every galaxy we see is moving away from us, and the further away, the faster. That's what Hubble measured, that's the Hubble law. That doesn't imply that we're the center of this expansion, because if you transpose your perspective to any other galaxy, you'd see the same thing. So the more factual statement is that every galaxy is moving away from every other galaxy. And if that's true, then no galaxy is the center of the expansion. Either they all are or none of them are. But basically, there's no logical center to the universe based on observation. And what was the second? I forgot the second part of the question.
Sorry, the second part of the question was, is there a center of the universe, and how fast is the universe expanding?
And I'll treat these as separate questions. The second question is, how fast is the universe expanding? And that is measured quite well by observations on the ground. And actually, it was one of the 3 key projects that the Hubble Space Telescope did in the first decade of its work back in the 80s and 90s. The current expansion rate of the universe is measured in astronomers' units to be about 70 kilometers per second per megaparsec, which means every megaparsec you go out from the Milky Way, and a megaparsec is about 3 1/3 million light years, the recession velocity is about 70 kilometers per second. So if you go 3 1/3 million light years, you see galaxies typically moving away at 70 kilometers per second. If you went 3 times further to 10 million light years, they would be typically moving at 210 kilometers per second. That's what the current expansion rate means, and that's how it's measured with Cepheid variables, actually, which is the same technique essentially that Hubble used in 1929 to show the universe was expanding in the first place. So we still use that same method. It's been much refined over the years. There's some debate, some argument over the expansion rate. It's measured to a precision of maybe 5%. Astronomers would like better precision on that number, because there's a little tension in cosmology between the measurement of the local expansion rate, that number I just said, and the inference of the expansion rate from cosmological measurements of the microwave background. That's another topic.
The next question is from S. Gordon51, who would like to know, is there a place online where one can find a constantly changing 3D model of the solar system? I guess they mean something that's constantly updated. We mentioned like programs like Stellarium or places like Worldwide Telescope, but I wanted to see if you have any other thoughts or ideas for that.
Yeah, I mean, in terms of where you would find the objects in the solar system at any given time, the best of the planetarium packages, the professional versions of Stellarium and Starry Night Pro, for example, I mean, they use the ephemeris, which is the orbital calculations of the planets, to say where they're going to be in the sky, and they do that quite accurately. So these, these high-grade packages of planetarium software are actually pretty good. I think to get the true positions in three-dimensional space, you'd have to go to a NASA website. I don't know the URL off the top of my head, but NASA indeed tracks the positions in the solar system. And so they are likely to, in their solar system web pages, probably out of JPL, they're likely to have this information in detail.
Excellent. And I will see if I can find that while Professor Impey is answering the next question, and I'll post it in the chat. The next question is from Sorge, who would like to know, how did the Big Bang happen out of nothing, and what would have been present before the birth of time and, frankly, space?
No, it's a good question, and it doesn't have an answer yet. But the Big Bang is a very successful theory or model of the expansion of the universe from a hot, dense state about 13.8 billion years ago. But the Big Bang model itself is just a physical description of the universe since that time. It doesn't say in the model itself what caused the expansion, what was the precursor state, and how was it that space and time come to existence in one moment, perhaps from a singularity. So that's a limitation of the model, and we can't ask the model to do something it was never designed to do. So we're in the realm of speculation when we talk about what happened before the Big Bang, what caused it, what was the precursor state. Some people have speculated because of inflation, the idea that the universe really emerged as a quantum fluctuation, because at one point the universe was smaller than a subatomic particle. That leads to certain kinds of speculation based on string theory or vacuum energy as a genesis of the universe from a quantum fluctuation in the vacuum. These are speculations. So there are, crude theories. I'll call them crude because they are not based on physics we can test in the lab for what may have happened before the Big Bang. And some of these theories imply a multiverse. They imply an endless succession of space-times coming in and then going out of existence or eternally. It's eternal inflation is the name for this. It's a modification of the inflationary idea. There's no evidence to support those particular theories. So I just want to be very clear that talking about the cause of the Big Bang and before the Big Bang is the realm of speculation in astronomy at this point.
Certainly. The next question is from one of our live viewers, Parzival Fusto again, asks, as human beings, why should we explore the cosmos? Just for curiosity or letting us know the answers? With that money, couldn't we build a whole new technology to preserve the Earth's environment?
It's a good question, and it comes up from time to time of why we spend money on what we do in science. So first, I'll give a little perspective that the money, and I can't speak worldwide to the numbers, but I can speak for the United States R&D investment. For the amount of money that the United States spends on astronomy research, astronomical research, is less than 0.1% of the federal R&D budget, less than 1 part in 1,000. So I would go so far as to say quite strongly that I think at that level of investment, it's totally worthwhile, that we're not wasting money or spending too much on it. Far more money is going into genomics research, climate change research, things that will affect human life and well-being, and hopefully the well-being of the planet. So in perspective, astronomy and astrophysics doesn't really get that much money. Some of it's raised from private sources as well, especially some of the large telescopes that are being built now. And so I would defend that. And yes, it is for curiosity. It's part of the human condition, if you like, that we wonder about our origins, our place in the universe. And, we cannot just get our sustenance from food and from other daily things. We also need to have a larger view of our purpose on the Earth and where we fit in the scheme of things. So I think astronomy fuels that and gives sustenance to those curiosities and desires to know about our place in the scheme of things. And it has value in that regard too.
All right, the next question is from Theo Laub, who sent an email, and we've got a graphic that I will pull up while you're explaining this to help show it a little bit. But Theo is having difficulty imagining the angles between the ecliptic and galactic planes. And so I was wondering if you could maybe explain with words the difference between things like the ecliptic and galactic, and then the equatorial planes, and then we'll bring up a graphic to help show it.
So in positional astronomy, there are essentially three reference frames, three sets of angles and orientations that you have to consider. The first and most obvious one is defined by the spinning Earth. So the Earth spins, and that means you see a particular set of stars overhead going around the night sky, and you can project the Earth's equator out into space, and that defines one reference frame. So that reference frame is an equatorial system, which makes the equator the reference for going around the circumference, and then the angle away from the equator towards the pole is the second angle. So that's the equatorial system defined by the Earth's rotation. The second system is coordinates defined by the plane of the solar system. So the Earth spins with a 23.5-degree tilt. And so the equatorial plane, the ecliptic, is tilted by 23.5 degrees from the projection of the equator into the sky. So that's a second reference frame defined by the planets orbiting the sun, as defining that azimuthal angle, and then the angle up from that to the pole being the second angle. And a third reference frame is defined by the stellar system we occupy, because the Milky Way has a preferred axis. It has rotation, it has a disk of stars and gas, and so you can define the galactic equator, which is that disk of stars and gas, and then the galactic poles, which is 90 degrees away from that. So that's the galactic reference frame. And so that has a different angle. That again, it's not the same angle as the ecliptic, and it's not the same angle as the equatorial system. So these are the three reference frames of astronomy, and they have specific angles between each one.
And I know that, Chris, you can't see the graphic that we are showing, so I'll just point out. So if you look at the North Galactic Pole in that image, and then that is pointing straight up in the image, and then the North Ecliptic Pole is the plane of our solar system that is pointing sort of to the left at a sharp angle, and then the North Celestial Pole arrow is pointing at a different angle, and that's the pole of our Earth. And then, so anyway, all of those different orientations are what give us those different sort of paths through the sky. So thank you very much. The next question is from Astronomy Interested, who has kind of a historic or philosophic question. Do any claims of astrologers have scientific proof or evidence? So I think we can also talk about like the how far astrology goes back, and
Right.
Ancient astrology versus modern astrology.
Yeah, so astrology has a long history as a human activity. It goes back with astronomy thousands of years, and astrology was done for emperors. I mean, through the early history of astrology, the divination, the sort of prediction of the future, if you like. The idea of astrology as determining personality is a more modern idea, but the idea of astrology as being used to predict the future was originally applied only to rulers and kings. So in Egypt or Mesopotamia or Babylonia, these early civilizations, astrology practices were used to try and predict the future, to be fortune telling using the positions of the planets and the stars. And so out of the gate, I'll say that there's no scientific evidence that that's a meaningful thing to do. The positions of the stars and the planets at the time of someone's birth or at different points in their life are determined purely by the orbits of these objects and by these astronomy measurements. They have nothing to do with the events of human existence or an individual human. So there's no validity to it. But it stuck for a while, and by the time of the Romans, actually, astrology started to penetrate into the population, with aristocrats, I think, being able to afford astrologers. And then, of course, in the modern era, we have astrology for the masses. Was omnipresent in tabloid or even respectable newspapers, magazines, websites, etc. And it's quite a business. I remember a New York Times article estimating 5 or 6 years ago that it's a multi-$100-million a year industry, astrology, in the United States alone, which I think is a little unfortunate because it's pseudoscience. It's not real science. People are essentially wasting their money. If it makes them feel better, well, okay, fine. Maybe it's not harmful in any obvious way, but it's essentially a scam, I would say. That's a strong word, but I'll use that word. People want to know the future. It's also interesting to know why astrology has traction. I mean, it's attractive to think that astrology can tell you something about the future, or it matches your personality, or can predict compatibility with your partner, and so on. there's a very strong effect in psychology called confirmation bias, where in all the totality of twists and turns of life and things that happen and don't happen, you tend to remember the things that happen that were mentioned previously, and you tend to forget all the things that may have been mentioned previously that don't happen. They just go out of your mind. And so there's a very strong bias called confirmation bias for humans to latch on to something that was mentioned or predicted earlier that actually comes to pass. But that's not a correct statistical basis for judging astrology. When the actual experiments are done in a controlled way, they find that it has no validity to predict the future or personalities.
All right, the next question is from Ravenwolf, who I think has a very timely question. There are very few astronomy degrees available in an online-only format. With COVID-19 moving so much instruction online, do you think there will be increased opportunities for those of us who would like to pursue an astronomy degree but need to do so online? This person is an adult student with a family, so they can't just move states for college.
No, that's right. I mean, astronomy is a niche subject, and so the number of institutions offering astronomy degrees has always been limited. And so it has been the case that to do an astronomy degree, you have to go to a relatively small number of places in the United States or in Asia or Europe or South America, wherever it is. It's finite, and it's very specific. COVID and the pandemic are going to change that probably forever, because so many things are moving online that whole degree programs will be moving online. At the University of Arizona, where I work, we're already in conversations about taking our bachelor degree in astronomy online. Would have to be done coincident with the physics degree going online, because most of our astronomy majors are double majors in physics, so we do it in conjunct with the physics department. So this is happening around the world. As we speak, there's still only a handful of fully online astronomy degrees. I think Swinburne University in Australia has the longest standing one, and they actually have a master's in astronomy that's online too, and it's a high repute program. But it's really still just a handful. But I would guess that within a year or two, there'll be dozens of these programs. It's not always easy to do a science degree online, because how do you do the lab component? How do you do hands-on work? It's the problem all science classes are having during the pandemic. But that will still happen. So I think we can expect astronomy degrees to start appearing online pretty soon.
The next question is from Qzom. Will the James Webb Telescope help us see what was there before the Big Bang?
Not really. There's no way to see before the Big Bang. Our vision of the universe runs out at the Big Bang. That's a singularity in the theory. It's an infinite cusp of density and temperature, and so it's a complete wall. But in practice, we can't even see that far back. The edge of our vision at the moment of any observing of electromagnetic radiation is the microwave background radiation. That was released when the universe became cool enough that stable hydrogen atoms formed, and the temperature was about 3,000 degrees, and the universe was 1,000 times smaller than it is now, 400,000 years after the Big Bang. That's our limit of vision in any kind of electromagnetic radiation. The James Webb will see back to what astronomers call first light, which is looking back in time to the point where the first stars and galaxies formed. And that's a very exciting thing to be able to do, because the universe essentially had what we would call a dark ages between 400,000 years after the Big Bang, when we see microwaves left over from the Big Bang, and the first stars and galaxies. When was that era of first light? That's what James Webb is partially designed to answer. We're going to guess that it's about 100 million years after the Big Bang. But James Webb should be able to pin that down. And that's really as far as we can see back with light, because before there were stars and galaxies, there were no luminous objects to look at in the universe.
The next question is from Foucault 33. What is the Big Crunch, and when will or could it happen?
The Big Crunch was an idea that in the time when we didn't know what the future of the universe was, because we hadn't measured its contents well enough, it was speculated that the universe might have a positive curvature, and that would imply that it would reach a maximum size and then recollapse. and lead to a sort of reverse of the Big Bang, a mirror image of the Big Bang called the Big Crunch, where everything squashed down by gravity to another singularity. So that's a classic Big Crunch, and it was on the table for a while, but by the 70s and 80s, it was pretty clear there wasn't enough matter, content of the universe, to slow the expansion down and overturn the expansion and generate a contraction. So the Big Crunch went off the table probably in the 70s and 80s, and it went further off the table in the 90s when we found dark energy and measured accelerating expansion, making it even less likely that the universe is going to recollapse. So at the moment, there's no evidence from the universe we live in that a Big Crunch is ever going to happen.
The next question is from Bill 2656. Can giant telescopes, I'm assuming professional telescopes, be configured in a way that allows simultaneous streaming to the public via the internet while astronomers are using them? If so, why isn't that being done?
It's there. You're right that the live telescopes that you can find online tend to be small robotic telescopes. The biggest telescopes tend to be used by researchers for their own means. I mean, the first practical answer to that question is that the real-time observing at most major observatories is not that exciting. Typically, astronomers are using charge-coupled devices, CCDs, with or without spectrographs, to take long exposures of very faint objects. They need the big telescope. The objects are far away, very faint. You have to gather light for an hour, 2 hours, half an hour. So there's very little happening in real time. When the image is taken, I mean, they are put on the internet, not always for public viewing. So that's something that will happen more. The project where this will happen really in a big way is what used to be called the Large Synoptic Survey Telescope, LSST, now renamed last year the Vera C. Rubin Observatory down in Chile. And this is a survey telescope using one of the mirrors built at the University of Arizona in our mirror lab to survey the entire sky to Hubble depth every few days. And they, because of the funding that comes partially from the National Science Foundation, from taxpayers, they've made a commitment to put that data online live and in real time as it takes data. Now it'll have to be filtered and compressed because it's 30 terabytes a night, so it's not anything that a normal person could handle or download. But that is a project coming up and within 5 or 6 years where you'll be able to see all of it in real time as you go. And if supernovae are going off or quasars are varying or objects are changing, because that's what the project is designed to do, to look for, you'll be able to hear about it. Other large telescopes don't tend to put the data online publicly, and there's a sort of competitive reason for that, because these telescopes are used by astronomers from the host institution, the institution that owns the telescope, or they apply through a very competitive program through a national facility to get data that they have privileged access to, typically for 12 months. They have a year to publish the data and not be scooped by someone else. Now, not that members of the public are going to scoop professional astronomers by looking at the data, but they might. And so, you know, the proprietary period for data at many telescopes still exists, and that's part of the reason why they don't make their data live online.
The next question is from an email. Wendy Traver asks, do astrophysicists think that just as the Higgs field induces mass in matter particles, that it also induces mass in dark matter?
That's a good question. And yes, in the sense that the Higgs field or mechanism is the mechanism by which mass is ascribed to all fundamental particles, inasmuch as we still think that the dark matter particle is a fundamental particle, as yet undiscovered, then yes, the Higgs field would attribute mass to that particle too. We don't know what the particle is. There's still a reasonable guess that the particle comes out of a supersymmetry theory, where there are counterparts to fermions and bosons, that is half integer and integer spin particles, a set of shadow particles, if you like. And in supersymmetric theories, which combine three of the forces of nature, these supersymmetric partner particles, there tends to be a lightest stable supersymmetric twin, which is in the mass range that would make it appropriate to be dark matter. And so that's a classic candidate for the dark matter particle. And yes, in the modern standard model of particle physics, the mass would have been attributed by the Higgs mechanism.
The next question is from Surge, who asks, does antimatter have negative mass? And is it related somehow to dark matter?
You can think of antimatter as having negative mass. It's essentially, it's a quantum property where it has an opposite quantum property. It's not as simple as a negative sign, I guess is what I'm really saying. It's an attribute, because masses don't subtract in a simple way, right? So it's an attribute, a quantum attribute of matter that leads to when the two come into contact, the energy being created as the mass is destroyed. That's antimatter annihilation. So it's, in that sense, it's an opposite quantum property. It's not like dark matter, however, because dark matter is likely to be a fundamental particle as yet undiscovered, quite a massive one that doesn't interact with electromagnetic radiation. Otherwise, we'd have seen it long ago. And it's a normal particle. It's an unusual, exotic, fundamental particle, but it's a normal particle. Now, dark matter will have its own antiparticle, too. So antimatter exists for the dark matter particle, too, just as it does for protons with antiprotons, with electrons, with positrons, neutrinos, antineutrinos, and so on. So we would anticipate that.
And the next sort of final part of that question is, are there technologies that currently exist that can detect antimatter?
Sure, we can detect antimatter. The classic way that antimatter was detected back in I think the 1940s, I think the Nobel Prize went to physicist Anderson for the detection of a positron, because the dark matter behaves differently from normal matter. So the classic detection of antimatter, which was its discovery and led to a Nobel Prize back in the 40s, was in a cloud chamber where fundamental particles created in interactions by smashing particles into each other send tracks through a gas, essentially a super compressed gas, and then the gas is rarefied, and so the particle creates a nucleation track, which looks like a little cloud path, almost like a contrail of an airline. So that's a cloud chamber. And then when you apply a magnetic field to that, if the particle is charged, it will move, it'll curve in the magnetic field. And so electrons will curve in one way. And since a positron has the opposite charge and is positively charged, it'll curve in the opposite way. And it was by the curvature of its track in a magnetic field that the positron was first detected. And so that cloud chamber method is a sign of older detector technology. Now there are more modern types of detectors, but they often detect antimatter in the same way, by applying a magnetic field and looking for the motion of the particle in the opposite direction if it's a charged particle. That doesn't work, say, for a neutron. An antineutron has no charge, just as a neutron does. So for neutrinos and neutrons, you have to use a different method.
So kind of circling back to the previous discussion of streaming information online, Hamazuji would like to know, how do you store 30 terabytes a night? Where are these drives being stored, or what kind of network storage array is capable of that kind of growth?
Yeah, I mean, storage capabilities are improving fairly rapidly. The density, even though it's a kind of old-fashioned technology, what we would call just as computer hard drives, they've been increasing in speed and capacity at the rate of Moore's law, sort of doubling every 18 months. And there's no sign of that coming to an end, because these are very mature technologies and they're still squeezing capacity out of hard drives. So you can store 30 terabytes a night pretty easily on a set of hard drives, for example. There are other ways to store it too. I mean, the more exotic technologies like bubble memory have not really panned out on a commercial scale. So basically, it's just the cutting edge of pretty standard commercial technologies, just scaled up to sort of industrial strength, that are used to store this amount of data. The problem for these telescopes with huge data rates is not really the storage, it's the transmission, it's the capacity of the internet and the bandwidth of the internet, because this data in Chile has to be got to the United States and around the world to collaborators, and essentially it has to be done with optical fiber. The business of beaming that kind of data to a telecommunication satellite and sending it around the world, those bandwidths are just not really good enough. So basically you're using optical fiber where the capacity can be enormous, and that's how it's being done.
All right, we are getting near the end of our session. I think we have time for a couple more questions. But as we wind up, I wanted to mention to folks that are on with us that if you have the opportunity to, or if you have the capability to subscribe to the channel, that would be fantastic. We always appreciate the help, and it helps us keep doing these programs and keep doing high quality programs. If you have an Amazon Prime subscription, you actually get a free Twitch sub. And at some point in the future, we are going to do a little tutorial on how to figure that out and how to find it. The next question is from Parsival Fusto, who has another great question. Is it true that objects or space outside the Earth smells different? So people have said that Mercury is odorless, Venus smells like rotten eggs, the moon smells like gunpowder. And I believe I've heard astronauts say that it smells like something burning when they come in from spacewalks. Can you talk about why it smells different in these different places, or why we say it does?
Right. That's an interesting question. The smells of space. Space does have smells, but not the vacuum. I mean, smell obviously is molecules with particular shapes hitting receptors in our nose or our olfactory system, creating the sensation of smell and odor and taste and so on. They're associated, of course, and that doesn't happen in a vacuum. So the moon, you know, on its face doesn't have a smell because it's a vacuum, and so, you know, there's no air, no medium to carry that smell. However, you know, lunar dust does have a smell. So as astronauts, you know, brought lunar dust into the capsule, for instance, during the Apollo missions, it came into the capsule, which had air that they could breathe, and they could smell the nature of the granitic particles or the lava or the various types of geology that the particles are made of. So you know, rocks of different types do have a smell. Venus definitely has a smell, has a very thick atmosphere, and yes, it does have the rotten egg smell. It has hydrogen sulfide, it has some sulfur dioxide. Mostly it's carbon dioxide, of course, but it also has some rather unpleasant chemicals. It has cyanogen and acetylene. Both of those are extremely toxic. Acetylene, I think, has no smell, actually. It's just deadly. So yes, different space environments do actually have different smells. If you want to extend this further, so near the end of our time here, we can get a little lyrical. In the regions where stars form, that is a very low density medium, but it's not a vacuum. It's like 1 or 10 atoms per cubic centimeter, I suppose, which is a billion times less than the air's density you're breathing. In these regions where stars form, molecules are quite abundant, and there are all sorts of molecules. There's ethyl alcohol, for example. So some star forming regions will smell like rotten apples. Some of the chemical ingredients that we use to synthesize banana smell on the Earth also exist, one of those molecules. So there are actually, you know, some very familiar smells that might occur in the interstellar medium if you could somehow breathe that gas. Unfortunately, it's too diffuse. It's essentially a perfect vacuum. So if you're in that medium unprotected, you would die. But in principle, yes, the interstellar medium has probably the most interesting smells of glycol and so on, of all the mediums we can imagine in astronomy.
All right, and as we wrap up, this will be our final question. Student McLeod asks, in the proton-proton cycle reaction in our sun's core, does the positron that escapes during the first fusion step annihilate along with a free electron, further driving up the core's temperature?
Yes, that's a good question, and it does. So when you create antiparticles in these fusion reactions, now the antineutrinos are also created, and they just escape the situation because their interaction rate is so low. But positrons, yes, will almost immediately encounter a free electron in the plasma and annihilate. And that's essentially built into the equilibrium calculation of the fusion reaction. So since it's a routine byproduct and that annihilation is a routine occurrence that occurs very, very quickly after the initial fusion reaction, it's essentially built into the calculation. And it does, yes, add a little energy and therefore a little temperature and pressure to the interior of a star. And if you don't include that process, that annihilation process, you actually get the calculation slightly wrong. It was a good question to end with. Thanks for your questions. Very interesting and varied as always. Thanks to Vicky for helping with this transmission, and for Matthew, and behind the scenes, Alexander's always at our side. So hope to see you all next week. We'll announce the next couple of sessions soon.
Excellent. Thank you very much, everyone, so much for joining us. Couple of quick reminders. We've got an amateur astronomy session that's coming up on Friday. And on Monday, Victoria will be reading the first few chapters of Einstein's Monsters. So, Chris, maybe you can give just a quick overview of what that book is and why we're excited to be doing that.
Yeah, we're starting to do sort of book club, if you like. So Einstein's Monsters is subtitled The Life and Times of Black Holes. It's a book I wrote about 2 years ago. About black holes large and small, about general relativity, about what we do and don't know about black holes, speculation as to their role in the universe, what happens to space and time near them, what would happen to you if you fell in, and so on. So there's quite a lot of black hole stuff that people I know are interested in because these questions come up in our live sessions quite often.
Excellent. And for those of you who are still around, we're going to raid the CosmoQuest X channel. Thank you all so much for joining us. Have a great rest of your week and weekend.